So here we have the JEOL JEM F200 microscope. It's a cold field emission gun TEM operated at 200 kV. This instrument is also equipped with an EDS detector. If you remember, in the previous lectures, you've seen an example of the 2100 TEM, which has a lanthanum hexaboride filament. If you remember your lessons on the types of emitters, you have thermionic emitters, you have Schottky FEGs, and then you have a cold field emitter. So the idea is, this cold field emitter has a tungsten filament which is maintained at room temperature, and every day you want to use the instrument, you do a quick flash. So when you flash, what you do is you remove any oxide or a redeposited layer on the tip of the filament, and this is an automated process now. Earlier this was all manual control and through turning of many knobs, and it was more difficult to maintain a cold field emitter. But thanks to the automation now, you can actually do a flashing every day. Although the stability of a cold field emitter is much lesser than a thermionic emitter, or in comparison with a Schottky emitter, the stability is not as good. You can actually do multiple rounds of flashing through the day and then still keep the instrument running. The advantage is the FEG, the gun assembly, the FEG itself has a significantly longer lifetime than a Schottky FEG. So here is where your field emitter is, and this section consists of your condenser lens, the objective lens, and the apertures. In this instrument, all the apertures and everything is concealed, you do not see them. Here is where your specimen holder goes into the microscope. You have the illumination lenses again here, the binoculars and the fluorescent screen over here. Now, this instrument also has a fluorescent screen camera. So you have a camera which is pointing towards the fluorescent screen here, and you can record and see the live images on the fluorescent screen on the microscope computer. If I go down, going back to the layout that we saw, whatever is concealed here also contains a CMOS camera in this particular microscope, and if you move here, the layout is pretty much similar. So this is how the high tension tank looks like, and you have some water flow controllers here. Here's where the chill water comes from the chiller, similar to a system that you saw in the previous videos. And then all of them are here to control the flow rates to different lenses. So you have water cooled lenses in this instrument as well. And if I go to the other side, you have the electric control. So similar to the way you saw on a 2100 microscope, you can read the sputter ion pump readings here. So even this microscope has a roughing pump, which is typically a membrane pump or a scroll pump, and then this is kind of a backup pump to the oil diffusion pump. Even this microscope runs on an oil diffusion pump. Alternatively, you would have FEG instruments which also run on turbomolecular pumps as well. And once the oil diffusion pump achieves a vacuum of something in the range of 10 to the minus 5 Pascal, you have 3 sputter ion pumps, or the other manufacturer, Thermo Fisher, calls them the ion getter pumps. So you have a 200 liter sputter ion pump which is connected to the gun chamber here, and in between the gun and the column you have another 150 liter sputter ion pump, and on the column where the specimen area is, you have another 300 liter sputter ion pump. So the idea is, in a cold field emission microscope, which is extremely sensitive to ultra high vacuum, to have more stable emission, you would want to maintain as good vacuum for as long as possible. And this is achieved with a combination of several sputter ion pumps as well. So in this system, you have 3 of them. Now the layout is exactly similar, and the operation sequence is also similar to the other microscope that I told you. The additional modes that you can do in a more reliable way here are, you would do high resolution imaging, and you would also do STEM imaging with EDS mapping. When I talk about starting to operate this instrument also has something called as the spec porter. In a couple of minutes, I'll show you what's the function of this. So here you can automatically load the holder into the microscope. So once you carefully load the specimen into the holder, it goes in automatically. Bear in mind, not all holders are compatible with the spec porter. You should check for the compatibility. Typically an indication is this gray back that you have here. So with that, once the holder is inserted, I will start by aligning in the same sequence, starting with the condenser aperture and aligning the eucentric height, and then depending on the modes of imaging, I will correct for the astigmatism of the objective lens, or if I am doing STEM mode, I will first correct for the astigmatism of the condenser lens. So here we have the single tilt holder, and we've loaded a gold cross grating sample in this. It's a standard sample which you use for calibration of the microscope. One of the reasons why I want to put this in is just to show you some of the possibilities on this microscope to do high resolution TEM and STEM. And for diffraction and tilting, I'll show the same on another aluminum sample a little later. Now, one important aspect is, although you may have some camera calibration that exists, to get reliable diffraction data, it is always advisable to stick to one particular camera length of your convenience depending on your material system you're studying, and then use such a gold cross grating sample to get reference diffraction patterns. This always helps you in getting rightly calibrated diffraction patterns. No matter what accuracy you have in calibration, it is always better to have your own safety backup values to ensure the data you're measuring is accurate. Now I'll just show you how the specimen is loaded into the, how the specimen holder is loaded into the microscope. So this is in. You can operate this in a manual mode as well if required, but once I just put it in and I select the appropriate holder, this starts pumping down. So the specimen chamber was at 252 microamp and it just started pumping it down. You can see that once all the vacuum values are actually in the order of 10-6 or 10-7 or greater high resolution vacuum, and once all of these are shown as ready, you can then actually insert the specimen holder and then you start pumping. So what you are doing automatically by flicking a switch on the other instrument, it starts automatically here and the values will go down, and once it is ready, the holder goes into the microscope column. So once this is done, it is advisable to close the clip and this chamber to ensure you have good drift stability. Okay. Now we'll look at the layout of. So this instrument has a slightly different layout on the console. You have these 4 parts of the console. The left panel, you have a few knobs, and then you have the tracker ball here, which is used to move the stage. You can choose the piezo control by selecting the superfine or coarse for doing coarser movements. You also have the shift X and shift Y knobs here. And then for tilting, you do not have the pedals like you have on the other instrument. Over here you have the tilt Y and tilt X buttons here, and this is to adjust the stage height. If I now focus onto the left console, what you have here is a button called multifunction button. So with this you can assign whichever functionality you want. At present this is assigned to the screen lift. So when I press this, the screen is retracted, and I press this back, the screen goes in. Here is where I open the column walls. So after I start the emission and the emission current is stabilized, I typically press this after inserting the holder. This is to neutralize and run a loop through all the lenses and to maintain closest to the standard alignment values. So you have the PLA button here. The PLA button is again for using to do the diffraction shift, or when you're imaging in STEM mode to move the STEM signal that you get, the forward scattered electron signal that you get, to the center of the detector. You have the condenser lens stigmation correction here, the objective lens stigmation correction, and you have the bright tilt button here. The knobs, if you see, you can assign different values to the multifunction knobs, and this is to make it coarser or finer. You have something to choose the convergence angle. In the other instrument, you had spot size and convergence angle as alpha, where you could select from alpha 1, 2 and 3. Even here it is similar, you can choose the alpha or the convergence angle here. The spot size you can vary from anywhere between 1 to 5 in TEM mode and 1 to 9 in STEM mode. The brightness that you see here is to adjust the intensity of the electron beam that is hitting your specimen surface. This is essentially controlling your strength of your condenser lens or the condenser mini lens. And the shift X or the shift Y here. So you have an equivalent knob on the other console and the deflection or stigmator knobs here. So these are analogous to the multifunction knobs you have in the Thermo Fisher microscope. So shift X and shift Y is to align the beam and to position the beam to the center of your screen. Deflection or stigmation, these knobs get activated once you select one of these options. For example, if I do PLA, then this is assigned to move the diffraction pattern, and if I have CL stig, I can correct for the condenser stigmation, and OL stig to correct for objective stigmation. If I focus onto the right side panel now, what you have here is to choose the different modes of magnification. So in the mag mode, so unlike in the other instrument where you had mag 1, mag 2 and SA mag, you only have one mag mode here, and then you have the low mag mode. When you switch into the low mag mode, you are also switching into the Lorentz mode on this particular instrument, and then you have the diffraction mode. You have the image wobbler and the HT wobbler here, which are used for doing some alignments when you want to do high resolution imaging. These two knobs are again shift X and shift Y, like I was mentioning a short while ago, to move the beam, and based on the functionality that is assigned, you can correct for your stigmatism or for adjusting the bright tilt or anything. Here, the magnification and the camera length, which is in imaging mode and the diffraction mode, is selected by turning this knob. So when I turn this, I can go anywhere from 2000 all the way to 1.2 or 1.5 million X magnification using this. Now here you have the image or diffraction focus knob. So the key difference here from the other console which you saw on the 2100 is, it is the same button to tune the focus for the objective lens, whether it is in imaging mode or in diffraction mode, to adjust the focus of the illumination lenses. I have this standard focus button here. When I press this, the defocus value becomes 0 and it brings close to the factory setting of alignment that is done. You have the detector offset and the detector gain here. These two knobs are useful in tuning your image brightness and contrast when you're obtaining STEM images. So this is about the layout that you have on the console. We will start with operating the instrument now. So on the Cold FEG TEM, whether you're looking at the NEOARM F200 or the F200 JEM F200, what you have is this interface where if I right click on this particular window, this will remain stable here. And the first thing that you do in the morning, if you have not done it already, is you start with a high flash. This is to ensure that your emission currents reach the preset value. In this particular instrument, the preset emission current value is around 15 microampere, and we've already flashed it once. And I'll just switch on the emission by doing this auto emission on, and you get this window. Do you want to start auto emission? Yes. And what you see here is you have two lenses, the A1 and A2 lens in the gun, and first by turning on the A1, you will see that the emission current starts going up, and once the emission current stabilizes, you want to sustain it at a preset value of around 7.41 kilovolt, and you maintain 15 microamp emission. After the emission is on, you switch on the beam or open the column walls by pressing this button. And what you see here is shadow from edge of the gold cross grating sample. The first thing I do is I spread the beam by turning the brightness knob, and I search for a sort of a thin area or a transparent area in the specimen. If I zoom in, I see the gold cross grating sample here. So once I've loaded the specimen holder, I'll switch on the beam, and you can see on the fluorescent screen camera here, you have to search for an edge of a sample or a hole. And what you can do is, if your instrument is maintained regularly and have preloaded alignment files, I can always load the previously existing alignment file. And then even after you load this, you should do some basic corrections. So the first thing that I would do to bring your area of interest into the eccentric height, or you could also start by correcting the alignment of the condenser aperture. So in this particular microscope, you can see here that there are totally 4 apertures. You have a 200 micron, 100 micron, 40 micron, and a 10 micron aperture. And you also have the objective lens, the objective aperture here, which are also 4 different sizes. And you have something called as the high contrast aperture, which is just below the objective aperture. You have the selected area apertures. You have the stem detector, which is going in over here. And what we'll do now is we'll first start in this particular sequence which we see here. So the first thing that I would do is by adjusting the the condenser aperture. So what I'll do here is I'll go to a hole, and I'll go to an area of somewhat like this. And let us say you go to a magnification of around 200,000 or 150,000 x or so. The advantage of having a FEG instrument is you can see that the crossover point is very narrow, and when I go to one side of the crossover, I see a sort of a shadow, or when I do this, I do not see the shadow. One way to know whether this sort of misalignment is due to your aperture being misaligned or due to any other effects, like on this particular instrument, the bright tilt correction which needs to be done. You have to bring this to the center. Let me show you a cross line to guide this. Now, ideally, this crossover point, when I go on either side of this by turning the brightness knob, should remain fixed at the same location. It is more or less there, but let us just see what happens when I correct this. I can move the aperture here through this particular button here. It is automated. As you see, the Once your edge of the aperture is concentrated in bright line here, you can assume that the aperture is more or less centered. You can see there's a little difference here. So the aperture is centered with the crossover point, and the next step I do is I bring the specimen to the right eccentric height. So for this, I go to the area of interest on my specimen, which is somewhat like this, and I go to a magnification of around 25 to 50,000x. The same way I corrected the eccentric height by using image wobbler in the other instrument, I do the same procedure here. Please note that when I change my intensity knob now, your image is actually moving and it is not fixed at one position. This is an indication that your specimen is not at the right height. So I can press standard focus once to ensure that my lens current is set to the eccentric lens current, and now I press the image wobbler button and I can change the height by using the Z knob, or the Z button. I have increased the Z from close to 0 micron to around 40 microns now, and I see that the image, when it is being wobbled, it goes more or less up and down over a plane, and at this point it starts coinciding, and at this location where I see the minimum contrast, you know that you are at the right eccentric height. After that, I unpress this image wobble button and I am good to go with imaging. To obtain a bright field image on the camera, I have to center the feature of my interest onto the screen, and I spread the beam large enough or wide enough such that I do not cause any damage to my camera. And before I lift the screen, I go to the software here. In this particular instrument, it's called the Radius from MSys. I can switch to the live mode. You have the automatic or the manual modes. It is always suggested to go with manual mode with 200 or 500 millisecond exposure time to just be on the safe side to start with. So I can click on live and I see the image on my screen. So if I want to record a bright field image, I just get this. In order to get a bright field image with the objective aperture on and to improve the contrast, what I do is I insert the screen again, I spread the beam in a large enough area, I press the diffraction button, I now bring the diffraction to the right focus. As you can see, at one point you see the rings. I'm not looking in particular for any specific kind of an image, but just to enhance the contrast, so I can put in one of the objective apertures of 60 micron in. So when I click this diffraction button, what I'm seeing here is already the back focal plane of the objective lens, which is where your objective aperture is lying. And when I click insert, the aperture goes into the plane. The aperture is more or less centered with the center of the diffraction pattern or the brightest spot, and I go back to image mode again by pressing mag, and let us see how the difference in the image is when I put in the aperture. So Here the image on the right is with the 60 micron aperture in, the image on the left is without any objective aperture in. There is no significant or noticeable improvement in the contrast as yet in a direct comparison. So let me just put in a slightly smaller aperture and then show you how the image quality improves. I'm ensuring that the objective aperture is alright. So the image on the right again is with the aperture on, and the image on the left is without the aperture on. I see some difference in the gray levels in this carbon area in comparison with this area. So the contrast between this point and this point is more in this image than here. Now this is one useful or a handy way to enhance contrast in some of the materials that you might use for imaging, especially when you're using low atomic number, low Z materials, or even in metallic samples when you want to highlight a few specific features or a few specific grains. This comes in handy.